Our next speaker is Adriaan Vorster. His topic is Architecture, the Language of Complexity, a System Engineer's View. Following a successful career in electrical engineering research, Adriaan moved into the ICT field, where for over 23 years he's been involved in business systems analysis, design, development, and implementation. He then joined GMSI and worked with most of the gold, platinum, manganese, and iron miners in South Africa on the development and implementation of master systems plans. During the latter part of 1999, he developed the first value chain-based mining architecture for the Mineral Resource Management Division of AngloGold. This work formed the basis of the Open Group's M Business Process Reference Model for exploration and mining. Adriaan served as CIO at the University of Johannesburg and a number of other organizations within South Africa. One of Adriaan's key catchphrases is, "You're never too old to have a happy childhood."
Good afternoon, and thank you for joining us today. We are talking about architecture, the language of complexity. Initially, I will set the scene that speaks to the complexity of the systems that we are working in today. Now, what's really important, I will not dwell on the minutiae of what I'm talking about. I would assume that stuff like the Zachman framework, Lehman's laws, and the Kneven framework is well known. If not, there are several sources of knowledge on these, and I would really urge you to refresh your knowledge on these wonderful artifacts that's been developed over time to allow us to manage the complexity of where we are going with our systems and our environment. So the first thing I'd like to do is look at the definition and purpose of architecture and the early indications of complexity, as was stated by Brooks and Zachman, and then systems maintainability and Lehman's laws. And the common thread running through this is the complexity of the systems that we're working in. The Kneven framework as a management tool that allows us to identify domains with suitable solutions. And then looking at language and how we communicate. Then we'll be looking at the architecture as a description of complexity, and we'll have a conclusion at the end. I would like to start off with a standard definition of IEEE for 2010 of architecture. And what's important about architecture in this sense, it speaks about composites, it speaks about the primitives, it speaks about the relationships between them. And this is a well-known definition. But what this definition actually says is, what is architecture? It doesn't say, why do we use architecture or how do we use architecture? Now, how do we use architecture? We create a range of models. And why do we do it? Simply to allow people to comprehend and to converse about the complexity of the environment that we're working in. So the really important thing is looking at where we are going. Now, early on, Frederick P. Brooks, working on the IBM 360 system, he was the first person to create the term software architecture. In other words, in Brooks's mind, there was a construct within which he was doing architecture. He very soon identified a number of what he called inherent difficulties. Things that cannot be extrapolated away or cannot be subsumed. They are inherent to the domain. The first of which is complexity. The second of which is changeability. The systems that we develop are not bound by the natural laws, like we've got in physics, for instance. They are bound by periodic cycles of commerce, of fads, of fashion, of technology. So the changeability requires of us to continually change our applications and our environment and our organizations. Then he went on to talk about invisibility and unvisualizability. Now, this is very true, especially where we are now moving into very complex domains. It is very difficult, a priori, to determine what the outcome would be. So that was another important aspect that came to the fore. The other thing, of course, is conformity. The systems that we develop, the organizations that we structure, have to conform to a whole range of norms, from the social to the legal to the medical, you name it. We have to conform. And all of that has got a constant pressure on the architecture to continually evolve to suit these requirements. John Zachman, he developed the Zachman framework. Now, the Zachman framework, as all of us know, goes back to the 6 primitive interrogatives: the who, when, where, what, why, how. Now, what's important about those, there are no natural projections between a why and a how. In the why sense, you can make business rules that how your project won't be able to implement, for instance, or what your data won't support. So it is incumbent on the architect to keep on building the relationship between these 6 primitive interrogatives. And the important aspect, because there is no natural projection between them, in mathematical terms, they are considered to be orthogonal to each other. So the Zachman framework is not a planar structure. The Zachman framework represents a 6-dimensional hypercube. And that is a fundamental complexity of what we are dealing with. Another important aspect of a Zachman framework is working with the primitives. If you go right down to the bottom row, you are working with the primitives. And that is really important. I've got a structure analogous to this. It's the good old-fashioned periodic table of the elements. And that is based on the primitives of the elements. Now, I agree that Russell Ackoff said that people do not experience atoms, they experience tables. But unless you understand the primitives of the metal or the material that table is made from, you could wind up choosing material that will degrade, like using mild steel instead of stainless steel. So the knowledge of the primitives are really important. But the really important thing is that the Zachman framework, inherent to it, is the fact that the framework is fractal, which means it's got self-same replication, scale independent, as well as the fact that there are multiple feedback loops and linkages between the cells of the framework. Lehman looked at all of this and he came up with 8 laws. What Lehman said is that any system that is used will be changed. Users discover new ways of doing things. The way that you plan stuff to happen will soon be changed by the expectations of the users. The other thing that he said, unless you change, you are very careful with your change, you will increase the complexity of your systems. So the really important aspect is that there's a constant pressure for change. Lehman also noted that your systems include a number of feedback loops and a number of concurrent processes running in parallel, which means there's huge complexity. Now, Ivor Jacobson had a look at software complexity, and Ivor Jacobson modeled it very closely to the second law of thermodynamics, which is perhaps not a bad way to look at it. He started off by saying, let's take a system with known complexity S, and then we change it a bit. In other words, a resulting system, the change in the system will be similar to the system's complexity. So what we can say, there's a proportionality constant K that we can bring into this discussion. So if we look at the mathematics behind it, you've got a system and you introduce a small change. So you've got a system S, introduce delta S. And this changes over time. And when you integrate that, you get a very, very interesting result. That your system complexity is given by the initial complexity S0 multiplied by e to the term kt, where k is your chosen constant and t is the time. If we look at the trajectory of these over time, we will see that the possible trajectories are quite interesting. When we have a state that our constant k is 0, we have the blue trace on the graph. Nothing changes, which is consistent with what Lehman observed, what Brooks was talking about, and what you can see from a Zachman framework. If you change nothing, nothing changes. That's quite a trite statement. However, if you would choose k to be smaller than 1, what you will find that over time the complexity will decrease. This is a great environment to be in. But the real life environment shows us that we are never in that happy situation. in normal life, k always has a constant bigger than 1, which means that the complexity increases. So when we look at this complexity evolution, and what I've done here is I've plotted 2 graphs, and the only difference is at time 10, I introduce a 10% change in k. And what is important to notice from these graphs is that there is a limit of maintainability. And that comes about because complexity normally results in failure. The more complex things are, the more things can go wrong, the more likely it's breakdown. So you get to a point where the system is so complex that it so frequently breaks down that it's unusable. And that is known as a limit of maintainability. And what I'd like you to see from this picture is that any change that we make, as I did at time equals 10, I introduced a 10% change. And you can see the resultant shortening in the life of that software. So what we do when we change it, every time we touch the software's useful life decreases. The other thing, of course, is at time equals 10. If we were supposed to fit a bug fix or patch a security hole, and we didn't do it, we would, of course, instantaneously go to the limit of usability. The system will just crash on us. Now, what's really important is to look at the extreme right-hand side of this graph and notice the difference between the blue trace and the amber trace, where they end. Now, why I want you to think about that is that this curve, e to the kt, is very similar to the sigmoid curve, and that is called our S-curve. In other words, if your competitor introduces a new product at S equals 10, you will over time find that you are now part of his strategy. He has invalidated your strategy, and you have to see what you can do, because if you look at the difference between the blue and the amber traces, you are not heading for a good life. So what does all of this mean in real life? The systems that we build today, unless we are very careful, will become the legacy of tomorrow. And that legacy is the unchangeable elephant in the room. That is the one that causes us to apply quick fixes and other nonsensical attempts to make this elephant to dance. And in the same time, we are destroying the life of that system. So our best option is to have loosely coupled, self-contained units of functionality. And this speaks to what Martin Fowler calls the strangler program, where you've got an existing tree and something else grows over it and over time renews the tree. Our best hope is to understand where we are. And that becomes a very difficult thing because the study of complexity has given some great results. And I like this map from Brian Castellani because he goes back quite a while and he shows how the study of complexity has evolved into a cross-discipline field, starting out from system science, cybernetics, artificial intelligence, and dynamical system theory. And what we are seeing from this graph is how all the disciplines, whether it's in social sciences, whether it's in life sciences, whether it's in engineering, software, business, all of those are busy concentrating on one objective. And that objective is to make sense of where we are going. And in this slide, what we can see that the clustering of current cross-discipline fields of complexity studies are coagulating. And right there in the middle, we find the Cynefin framework. Now, the Cynefin framework, I assume all of you know what we're talking of. It is a sense-making framework. It has got 5 domains. It's got 2 regions, an ordered and an unordered region. And within those 2 regions, it's got 5 domains. The central domain is unordered. You don't know where you are, right? The left-hand domain, that's a rather interesting one because it's got complex domain and a chaotic domain. And we are much more familiar with the right-hand region. In the right-hand region, we've got the obvious domain and we've got the complicated domain. And the important thing is, in those domains, we've got external constraints that govern a lot of our experiences. We have got, in those domains, in the audit region, what we have got there is a good old-fashioned linear relationship. So expected outcomes are valid. The Newtonian analysis holds. This is very easy to work in because what we've got initially, if we look at the obvious region, what we have there is that everything is well known. If I pull on this lever, that action will happen. If I push on that button, that action will happen. If I tell this guy to do this, everything will happen. When we get into the complicated domain, things are not that simple. We are now in the domain of expert knowledge. We have to get experts around us to help us understand this. People that know certain aspects. Even though we do not understand the minutiae of, for instance, flow dynamics. We do understand turbulent flow and we do understand cavitation and all of these aspects. So we do have knowledge that allows us to model things and to find solutions. However, when we move into the unordered region, we are into the complex domain and the chaotic domain. In the complex domain, we have no way to determine what likely outcomes would be. We are in a situation where we have to send a probe and find out what's happening and then come back and do something about it. And so cause and effect are no longer connected. We understand things in hindsight. Case studies are not applicable. So in this environment, we have to be very careful what we are doing. And what we are seeing is that multiple experiments are being done to find a solution. And from those multiple experiments, we find regions of validity. And lately, we can use social network analysis and k-means clustering, small world approach, etc., to model those approaches and find our solutions or find the best fit illusion. But it's not obvious from the outset what the best solution could be. When we move into the chaotic domain, all bets are off. This is a situation where we've got to be very careful. What we see here is that we will carefully launch a probe and then be ready to either boost it or to shut it down. So we've got those two options. And the complicated, or rather the complex and the chaotic domain, are the big domains of learning. This is where learning takes place. Now, I've had a long military career. And in my world, the Cynefin framework translates in the following way. And it might be invalid for anybody else. But I see the obvious domain as boot camp, basic training. You are training people to walk in a line and to lift their feet up and down together. That's boot camp. When we get into the next domain, now we are moving into the complicated domain. That is where I see force preparation. That is the environment in which we've taken the people that have now proved mastery of a simple environment and we put them through advanced training. They do mortar training and they do artillery training and some become pilots. So they build on the previous experience, but it's in a contained environment. There are rules that govern it, the flight of projectiles, etc. Although not precise, we are very good at predicting where that would fall. The next thing, we plan an operation. And everybody knows there are two laws of operations. Von Moltke said that no battle plan has withstood first contact with the enemy. And there's another rule that says major battles always happen where maps meet or an overlap. So with that in mind, we've still got the initiative. We launch the operation. And when we fall into a situation, we've got the training and the backup, we can retreat into our known environments and from there determine the action. However, to my mind, the chaotic domain, That is a domain where you walk into an ambush. You haven't got the authority. You haven't got the initiative. You are reacting to something that happens externally to you. And of course, the first thing is to take control. In other words, when you enter the chaotic domain, be ready to either fight or flight. That's what you should consider there. And that is just my personal take on the Cynefin framework and how I framed it in my own mind. And what's important is to understand that these boundaries are not firm. These are thought boundaries. One of the techniques that has become very valuable, if you look at the complicated and the complex domain, the boundary there, the Scrum technique of software development. Because what you do there, you take a piece of code for a kind of functionality you want, and you go into from the complicated into the complex domain, and you test your code, and you come back and you say, okay, it's worked or it's not worked. Just remember that failure doesn't mean you have to stop. It just means the option you've chosen has not worked. You should look at another option. So that is the Cynefin framework. And what's important about the Cynefin framework, it gives us a sense-making tool. When you look at the Zachman framework, it is a classification scheme. You identify stuff and there are sufficient pigeonholes for you to put it into. But the Cynefin framework allows you to look at something and to ask yourself, how much do I know about this? And then to understand that there are many good solutions that might work in the complicated domain that do not work in the complex domain. And there you have to be careful. So let's get to languages and communication. It is very important to understand that languages are not just about the spoken or the written word, and that every language has got its own sense and its own grammar and its own construction. If you look at the English language versus the German language, for instance, the sentence construction is different with where you put the verb according to what your sentence wants to convey. So we have to be careful of those nuances when we start communicating. There is a very well-known model, the Shannon communication model. And this model originated from a technology environment, and it's been widely accepted in all the other environments as well. And what it is all about is that you want to convey a thought. There is a stakeholder that has a concern, and the stakeholder has to convey this concern. But the stakeholder could be somebody from the marketing or financial department, and he has to convey a concern to somebody who's in information security. So this person will shape that message according to their worldview, according to their context, according to their knowledge base. And they will encode it in a way and then transmit it to the recipient. Similarly, what we have on the recipient is somebody, the security expert, has got a security view. And his whole premise is, how can this system fail? That is what good security architects do. They look for failure. The rest of us in IT, we live failure, but they essentially look at. And so this person has to decode and has to construct meaning in his domain concerning what's happening in the other person's domain. And what this calls for is that we will synchronize our knowledge. So we need consistent models in our discussions. We need to be able to reference the same terminology. We need to be able to reference the same symbols. All of this has to be important because we want to convey the right message to the end. We all know the worst thing that can happen to you in systems development is the client telling you, this is exactly what I asked for, but not what I wanted. And that is what we are trying to eliminate with this process. And this is the solution. I'm very happy to say that I've been around this environment for more years than I care to remember. But what we've got, we have got well-proven, we've got robust, repeatable tools provided to us. And what they do, they allow us to take a concern and to place it in context through, for instance, our good old-fashioned TOGAF framework. From there, we can take it into the Archimate modeling language that allows us to express in symbols and words and relationships and domains what we are talking about. And then we can take it to the client, to the stakeholder, and say, here it is. This is how we map this. This is how we will architect it, and this is how we will implement it. So what we are looking at is a standard way of communication that allows people to speak clearly and to understand what's going on. So my contention is that the system complexity that we're working in is escalating. That's the good news. It's not going to get simpler. And what we need to do about this is realize that in order to build sustainable systems, we will have to build them in a compartmentalized fashion with well-defined interfaces that will allow us to piecewise renew systems as we go along. And fortunately, what we have, the Open Group has developed over time numerous standards, numerous artifacts that we could use. There are white papers, there's guidance in a wide range of topics. And that allows us to remain current and to master the domains that we're working in. So that's it for today. Thank you very much.